Hey, welcome back. This is now 12.2, and we're going to look at derivatives and integrals of vector value functions. It's probably one of the easiest things we'll do all semester. And that, if you already know how to differentiate and integrate, you pretty much are going to be able to do this, okay? Basically, the derivative of a vector value function is the derivative of its component functions. Right, they'll start back with the sort of difference quotient and taking the limit of that thing. So I guess we could start with a definition of the derivative of a vector value function. So basically, r prime of t equals the limit as change in t goes to 0 of the vector value function evaluated at t plus some change in t minus r of t all over change in t. And in order to compute this, you could just basically compute the, work with the components again. So I think it'll go something like limit as change in t goes to 0 of 1 all over change in t times r of t plus change in t minus r of t would be f of t plus change in t minus f of t, comma, g of, you don't need to write this out, plus change in t minus g of t, comma, h of t plus change in t minus h of t. Okay, and then if you distribute the 1 over t, I mean, this is just strictly definitions, right? Change in t goes to 0. Distributing that 1 over change in t, you get a bunch of difference quotients, and each one of those represents the derivative of one of the components. Right? So then you would distribute the limit through, because that's what we could do with limits. We learned that in the last section. T, change in t, h of t plus change in t minus h of t, change in t, this is taking a long time, that would equal the limit of f of t plus change in t minus f of t all over change in t, change in t goes to 0, dot, 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 right? 3 of the same components. That's what you're saying right here. That's kind of, I guess, what they're doing here. And then that'll just equal the derivative of f of t, comma the derivative of g of t, comma the derivative of h of t. Okay. So I guess, in practice, it'll be pretty simple. Geometrically, then, of course, there's, okay, so I guess this would be computationally. Those limits have to exist for the derivatives to be there. But anyways, geometrically, the derivative is going to be a tangent vector to the curve at some particular point. So if this curve is traced out by r of t, so our r of t is tracing this out, then any point right here, if you find the derivative of r of t, it'll give you a tangent vector going in the direction of travel. Okay, so assume we're going in this direction. Okay, so it's basically, back in Calc 1, if you had a plane curve, the derivative would tell you the slope of the tangent vectors of the curve. Now we're actually getting, I guess, an equation for, or a formula for these tangent vectors directly from the derivatives. Right? Anyways, let's take a look at, so what is this? This is just, you can differentiate by differentiating the components. Let's take a look at example 1. So basically find the derivative. And again, I just like to use a component form, honestly. And mainly because in WebAssign, if you want to use the IJK, you have to go to the calc pad. So it's just terribly annoying. Okay. So anyways, if you know how to take derivatives, it's pretty simple. The derivative of t is 1. The derivative of t squared plus 2 is 2t. And there it is. That's easy as pie. Okay. In particular, if they want you to find R of 1, and then, so sketching the thing, right? So if you eliminate the parameter, x is t, y must then be x squared plus 2. So x squared plus 2 is a parabola like this. And I believe we are traveling in this direction. So R of 1 is going to be 1, 3. Okay, so 1, I hope that's around 3 right here. So R of 1 is this guy. And then R prime of 1 will be the tangent vector at that point. All right, so that would be 1, 2. So how do I draw that? Well, I'm going to start at this point here at 1, 3. I'm going to go to the right, left or right by this amount. So maybe I should write horizontally by 1. Horizontally by 1, and then go up or down by this next component. So vertically rise or fall by 2. So in this case, they're both positive, so I'm going, I'll do it in blue. I'm going to the right by 1, and then I'm going vertically by 2. And unfortunately, I put that stupid arrowhead right there. Let me get rid of that guy. Okay, so and I don't think this graph is drawn very well. Let me try again. So it'd be like 1. Now I got to get back in the blue. Erase 1, and then up 2. So the tangent vector would kind of be like that. Maybe I should do it in another color so you can see it better. Oops. It should be like that. Okay. So you count over 1, and then you go up 2. Okay. Okay, and they did a little picture there for you. You could always go to calc plot and draw the thing. You know, the calc plot's even better because it'll animate it. Let's just go crazy and do this really quick. This is t squared plus 2. 3 years later, and boom, boom. Okay, and animate. Okay, awesome. So that's just the trace vector, but let's add in the velocity vector is what I'm going to call it. Okay. So, whoops, let's clear it out. And you kind of see, oh, it's going really freaking fast. See the little thing that's kind of like points in the direction of travel. Okay. Carrying on then, let's see what else they have for us. Not much, huh? They got carried away with taking derivatives. I mean, if you want the second derivative, you just take the derivative again. So, example 2, I guess. So they give you a vector right function, cosine t, sine t, 2t. So the first derivative, just take the first derivative of the components, negative sine t, cosine t, 2. The second derivative, just take the derivatives again. So this would equal negative cosine t, negative sine t, and then 0. Then they start throwing in some dot products and cross products. So that, what is this? This is A, this is B, C. R prime of t dotted with r double prime of t. So you're just multiplying and then summing the components. So negative sine times negative cosine is sine t cosine t. Cosine times negative sine is negative sine t cosine t. 2 times 0, so I add in 0. So plus 0. In this case, the sort of velocity vector and the acceleration vector here, the dot product is 0. Okay. D then, they want the cross product of the two. And see what happens in that case. So you got your I, J, K. List out the components. Negative sine t, cosine t, and 2. Negative cosine t, negative sine t, and 0. And I need a little more room, so I have to move this over. Okay, so again, I like to use component, angle notation. So blocking out that first column, cosine times 0 is 0, minus will become plus 2 sine t, comma negative. Blocking out the second column, 0 minus negative 2 cosine t, so plus 2 cosine t, comma, blocking out the third column, sine squared minus negative cosine squared, so sine squared t plus cosine squared t, and then we could simplify that. So we get 2 sine t, negative 2 cosine t, and then 1 from the Pythagorean identity. Okay. Yeah. Okay. They're going to give you a ton of sort of formulas with regards to taking derivatives of dot products and cross products. It just depends on what sort of setting you're working in with regards to your job and stuff like that as to which formulas will probably be important. So they give you 7, and maybe like you'll use 2 of them all the time. So I'm not going to force you to memorize all 7. That'd be crazy. But they're there. They can simplify your computations. So one big issue in this chapter is the computations just get out of control, especially when you're dealing eventually with unit tangent vectors and unit normal vectors. In those cases, you'll have, well, even in curvature, once we get to the end there, in curvature, you'll have like 5 or 6 different formulas you can use to get the answer. And you kind of have to figure out which formula you want to use that's going to be the quickest. Okay, so that's going to be hard. That's part of your job, though, as a student, to kind of figure out how to reduce the amount of time you spend working. Because obviously, if you get a job, that's something you want to be good at, right? So, you know, you'll get your feet wet with it. But yeah, I'm not going to force you to memorize these. They do come up every once in a while in proofs. So I'll try to remind you as we use them. Another issue they have, again, is smoothness. So we would have saw smoothness back in the polar curve section in Calc 2. Basically, if you have a cusp, it's not smooth because the derivative will have an issue there. More to the point, though, we kind of need to give that definition, I think. So this is the definition of derivatives. Derivative. We need smoothness. So it's not just about the derivatives being nice. You also need to make sure that the derivative is not equal to 0. Okay, so everything simultaneously equal to 0, because those are the places, if you think about the components as kind of parts of slope, if all of the parts of the slope, the change in y over the change in x, if those are both 0, you kind of don't know what's happening, right? That's like an indeterminate form. So smoothness, let's make it more concrete. Basically, the component functions all need, the derivative of the component functions all need to be continuous. And oddly enough, then, we require that r prime of t is not equal to 0, the 0 vector in particular, for any value of t in whatever interval you're picking to be smooth. Okay, I don't remember if they had like smooth problems in here. They may or may not have. Let's see. Yeah, so this guy right here, number 9. Find the intervals on which the vector value equation is smooth. So r of t is 7t squared, comma 8t cubed. So the derivative, just take the derivative of the component functions. Both of these functions are continuous everywhere, okay? But if you let t equal 0, they will both equal 0. So we need to exclude that from our sort of smoothness interval. So I would say it's going to be smooth on the interval from -infinity to 0, and then 0 to union, then with 0 to infinity. Union symbol there, sorry, butchered that. There we go. Okay, so that's it's really never an issue for us, but I just want to mention that it's more than just an issue of continuity of derivatives. This thing has to, this zero issue is also there. Okay, yeah, and then geometrically there'll be little cusps is what we're kind of looking out for. A bunch of derivative rules, so if you need to simplify computations, you can always look to those rules. They do some proofs of them. Using properties of derivatives. So for instance, the derivative of a dot product, you can kind of, it's kind of like a product rule, if you wish. So let's see if there's one like that, sure. So like 11 part D. So we have the derivative with respect to t of r of t dotted with u of t. Okay. So if you look back at the property, it'll turn out to be kind of like a product rule from Calc 1, right? So you leave one alone, take a derivative of the other, and then plus take the derivative of the one you didn't take the derivative of before, and then leave the other guy alone. Okay, okay, so let's kind of take a look at doing that. And these are both dot products. Sorry, I'll put a little dot product symbol in there. What are my guys? So r of t is t comma 5t comma t squared, and then u of t is 5t comma t squared comma t cubed. So the derivative then, this thing is going to be, I guess we should get the derivatives. 1, 5, 2t, and then the derivative of u of t. And like, it's almost easier to I mean, the derivative, the dot product is a scalar, right? So if you took the derivative of a scalar, you would get 0. So in this case, you need to kind of use the, well, I mean, these are functions of t, so that's not necessarily true. But if you were to compute it, yeah. Oh, okay, I'll just shut up. This is 5, 2t, 3t squared. Okay, so the dot product is basically the dot product between these two guys. So you get 5t plus 10t squared plus 3t to the fourth, and then plus the dot product between those. So you get 5t plus 5t squared plus 2t cubed. And of course, that would be 10t plus 15t squared plus 5t to the 7th. Okay. Sorry, 15t squared plus, this should be t to the 4th, 2t to the 4th. So what did I get? I got 10t, 15t squared, and then 5t to the 4th. There we go. Okay. Okay. But you can do it the other way around. You can always just take the dot product and then take the derivative, right? So that the dot product of r and u, these guys would be 5t squared plus 5t cubed plus t to the 5th, right? And then its derivative 10t plus 15t squared plus 5t. So you see what I mean? Sometimes, go to the formula, but if you're not even familiar with the formula, it may not even be worth it, right? Because that was a lot of work. Look at the amount of work I did here using their formula versus just taking the derivatives for taking the dot product and then taking the derivative of the dot product, right? I would rather do this, the non-formula version. And I think even when I did the homework, I was like, forget that. I'm just going to do sort of the not. Let's look at part F. I don't want anybody spinning their wheels on the homework. What the heck does this thing mean? They mean plug 5t in for t in r of t, right? So they want the derivative of 5t comma 5 times 5t. So wherever you see t in r of t, you're plugging in 5t, and then 5t in for t squared, right? So you get the derivative with respect to t of 5t, comma 25t, comma 25t squared, and then the derivative is 5, 25, 50t. Okay, so anyways, there's that chunk. Let's move on. Integration then. So section 3, integration. Pretty simple, but they can make it really annoying because of the constant issue, the constant of integration. So whenever you integrate here, the constant is going to be a vector. And so let me just give you sort of the practice version. So in practice, we're not going to go the Riemann sums or anything like that. It just turns out that you can integrate the component functions to get the integral of the vector functions. So the integral of r of t dt is just going to be the integral of the component functions, f of t dt, comma, integral of g of t dt, comma, integral of h of t dt, right? The bummer part, though, is this constant of integration. So let's take a look at example 5. And they want us to integrate t ij, just t3 dt. So, you know, it would be simple. It would just be t squared over 2 comma 3t. But sadly, you're always going to have to add on this constant. And now the constant is a vector. So, I mean, in reality, you could just write it as t squared over 2 plus c1, because c will equal a vector, right? c1 comma c2. So it may be easier just to write t squared over 2 plus c1 and then 3t squared, 3t plus c2. Okay. I believe in the software, when you go to do this part, they'll give you a little calc pad, and you can kind of do it that way. So let's do this annoying one here. Whoops, I don't want to, I've already submitted an answer. Oh, jeez. This is so helpful. Okay, so helpful, guys. I did it again. I want to practice another version. Oh, it's not letting me, no wonder. Okay, so I'll do that one. Number 14. Let's make this annoying guy the video quiz for the day. Video quiz, video quiz, video quiz. This is the second video quiz in video quiz set 3. And this is number 14 in WebAssign. And it basically just gives you practice doing integrals. Let me write down the problem on my notes, so I will have it for reference. So we have t cotan t t. Okay, so you're expected to remember things from calc. What is it? Calc 2. Okay, so integral of e to the negative t sine t, comma cotan t dt. Okay, so first off, I'm going to integrate that e to the negative t thing. And sadly, yes, I'm going to have to do integration by parts, unless you remember the tabular integration, which I never do. So I'm just going to do by parts twice. So u is from Leate, that would be the trig before the exponential, dv. And I have t, v is negative e to negative t, negative e to the t dt is on this other guy here. Du is going to be cosine t dt, so box that off. This will be u times v, so negative e to negative t sine t minus the integral of v du, so that will become plus integral e to negative t cosine t dt. Then you have to do by parts again, so u is going to be cosine this time, dv, e to negative t dt. V will be negative e to negative t, du will be negative sine dt, box that off. So this junkoid will be negative e to negative t sine t, and then u times v will be minus e to the negative t cosine t, and then minus the integral of v du, which will be minus negative times negative. And here will be positive, but there's always a minus in front at that step. So you get e to the negative t sine t. You note that you got back right where you started. So if you kind of look at this equation right here, just that part alone, like you're rewriting like e to the negative t sine t dt equals negative e to negative t sine t minus e to the negative t cosine t minus this integral of e to the negative t sine t. Remember, box these two guys just replace with a variable. Usually they use I, and then solve for I. So you would have I equals negative e to negative t sine t minus e to negative t cosine t minus I. Add I to both sides, you get 2I equals negative e to negative t sine t minus e to negative t cosine t plus your integration constant, and then divide everything by 2. And finally, you have the first component of that integral, negative e to negative t sine t minus e to negative t cosine t all over 2. Okay. So e to the negative t cosine t. They want you to use the vector for the constant part. So you're going to add the vector on. You can see on the right here, I have to add in plus c, and I had to use their calc pad to do it. Okay, so I had to go to the calc pad, vectors, and then use that button, but with a c in it. Okay. So literally, I would have to press this, and then put c there. Okay. Okay. The other integral then, the integral of cotan. If you don't remember the actual answer to the integral of cotan, you could always replace cotan with cosine t over sine t, and then do a u sub for sine t. So du would be cosine t dt. So dt is du over cosine t. And so this would be equal to the integral of cosine t all over u times du all over cosine t. And that would be the integral of du over u, which would be the ln of the absolute value of u, back subbing, that would just be sine t. So the second component, ln absolute value of sine t. And then you add in your vector plus c. Okay? And you can see that to the right, that's my answer. The way I got my answer written, I have the negative upstairs, but you can factor out the negative and then put it in front of the fractions. So that's kind of how I did it there in my answer. For some reason, it wouldn't let me put it in the, I think I screwed up. I usually use the vector notation, but for some reason I used the ij. You have to, I think you have to use these buttons for ij and k, otherwise it gets ticked off. Anyways, that's the video quiz, that section. Okay, so you can see they can make them really, really annoying. Let's take a look at one of the definite integral problems. Okay, so 0 to pi over 3. This is problem, I don't know, number 16 of secant t, tan t, and then 2 sine t, cosine t dt, right? Okay, so for these, you are evaluating each component on those limits of the integral there. The integral of secant tan is just tan t, and then you have to evaluate that from 0 to pi over 3, right? So it's like 3 integrals for the price of 1. Integral of tan is ln of the absolute value of secant t, or if you'd rather, negative ln of cosine t. And we have to evaluate that from 0 to pi over 3. And then this guy, I usually do a u sub on it, so I let u equal sine t, and then du would be cosine t dt. So you would end up with the integral, 2 times the integral of u du, and then you get u squared over 2, which would just be u squared. Back subbing, you would get sine squared t. So I'd have sine squared t evaluated from 0 to pi over 3. Evaluating tan of pi over 3 is going to be root 3. And then minus, whoops, that's secant, sorry. The integral of secant squared would be tan. This is just secant. Ugh, sorry about that. The secant of pi over 3 then is going to be 2. And then the secant of 0 is going to be 1. The secant of pi over 3 again. So you get ln of 2 minus ln of 1. And then sine of pi over 3 is root 3 over 2. Squaring that, that's 3 all over 4. Sine of 0 is 0. Okay. And then you just get 1, ln of 2, ln of 1 is 0, and then 3/4. Okay, so no big deal. They throw in some magnitudes there. So the magnitude is just the square root of the component squared. Sure, let's. And then they have some initial value type problems that can be annoying. Let's look at number 17, I guess. So get the integral from 0 to 2 of the magnitude of t, t squared dt. So we'll see this in the arc length later on. This is actually the arc length formula. It'll find the arc length of that curve from 0 to 2. And so magnitude is basically the square root of the sum of the components squared. So we have t squared plus t to the 4th dt. You could factor out a t squared. So it's basically just, hopefully you're going to get really good at doing integrals. Whoops, I got them reversed. T, whoops, 1. Someday I'll get it. I'll get there, guys. I can cross that finish line eventually. Then I can, so the square root of t squared, because I'm on the interval from a positive interval, I can rewrite that as just t. And I have the square root of 1 plus t squared dt. And then it's just a u sub for 1 plus t squared. So du is 2t dt. dt is du over 2t. So this will equal the integral of t times the square root of u times du over 2t. T's cancel, bring out the 1/2. Rewrite square root u as u the 1/2 du. So I'll have 1/2 u to the 3/2 times 2/3. So 1/3 back sub 1 plus t squared to the 3/2 evaluated from 0 to 2. Okay, so that'll equal 1/3 times 1 plus 4 is 5 to the 3/2 minus 1/3 times 1 to the 3/2, just 1/3. So I would type that in, unless they say how many decimals to use for your approximation. They want an exact answer. Okay, so you have to literally type that number in and say, I factored out the 1/3 in my answer. They do some antiderivative problems with initial conditions. So this is a definite integral. This is antiderivative with initial conditions. Okay, so let's look at example 7 in the book, and then we'll call it a day. So find the antiderivative r prime of t equals cosine 2t, negative 2 sine t, and then 1 all over 1 plus t squared. Okay, the initial condition is 3, negative 2, 1. Okie dokie. So basically you just have to integrate each term, and then you'll have constants that you need to solve out for. So r of t is going to be the integral of cosine of 2t. We'll have 1/2 constant floating around when you do your u subs. That would be 1/2 sine of 2t. The integral of negative 2 sine t is just going to be 2 cosine t. And the integral of 1 over 1 plus t, and we need constants, right? Plus c1, plus c2. And then 1 over 1 plus t squared is tan inverse of t plus c3. Okay? So to get C1, C2, and C3, you use the initial condition. So you're going to let, for the first part, t equals 0 and x equals 3, right? So you get 3 equals 1/2 sine of 2 times 0, plugging in 0 for t, plus c1. Sine of 2 times 0 is 0. Sine of 0 is 0. 0 times 1/2 is 0. So you just get 3 equals c1. And for the next guy, when t is 0, we want y to be -2. So you set the y component equal to -2. So 2 cosine of 0 plus c2. Cosine of 0 is 1, so 2 times 1 is 2 plus c2. Then you could subtract the 2 to the other side, so c2 is apparently -4. And then the last guy, t is 0, and we're letting z equal 1. Right, so I got 1 equals tan inverse of 0 plus c3. Tan inverse of 0 is 0, plus c3, sorry. And then c3 must equal 1. So your final answer for your r of t is going to be 1/2 sine of 2t plus 3, comma, 2 cosine t minus 4, comma, tan inverse of t plus 1. Okay, let's make sure I got it right. Yeah, I got it right. I think I got it right. Yep. Okay, is that it? Yeah, and then they go to the homework. Okay, so as usual, thank you for watching, and we'll see you next time.